Okay, so welcome back everybody to the second part of my lectures where we're looking at reaction mechanisms. Hopefully you remember from the first part that I said one of the classes of reactions we'd be considering was nucleophilic substitution reactions. So what we're going to do is look at these in detail, and we're actually going to see that the nucleophilic substitution reactions can be considered to go via two different mechanisms. And the first one we're going to think about is unimolecular nucleophilic substitution reactions, which we call SN1. So it's S for substitution, N for nucleophilic, and 1 for unimolecular. So in SN1 reactions, what we're doing is we're replacing a leaving group. So this is something which can pull electrons away and depart as a stable leaving group. So we're losing a leaving group, and that leaving group is then being replaced by a nucleophile. So overall, what we're doing is a substitution reaction because we're substituting the leaving group with a nucleophile. It's nucleophilic because it's a nucleophile involved, and it's unimolecular because there's just one molecule which is involved in the rate determining step. So what do I mean by that? What I mean is if we think about the reaction mechanism and we think about the arrows which will show us which bonds are breaking and which bonds are forming, then in the first step, what's happening with our starter material, which we can also call a substrate, is loss of a leaving group. So here we've got a carbon, we've got three different groups on here, X, Y, Z, it could be anything. We're losing the leaving group, and this here is called our rate determining step. When we lose that leaving group and it takes electrons with it, then this carbon here has lost electrons, so it becomes positively charged. So what we're doing is we're forming a real intermediate. It's a carbocation, and it's positively charged, and that's the first species which is formed in this rate determining step from the substrate. So if we remember a little bit about the structures of intermediates, this carbocation is actually flat. So we've got 120 degrees bond angle around here, and it's flat. So if you think about the nucleophile coming in, which happens in the second step, because this is flat, the nucleophile could attack above or it could attack below. And because it can attack above or below, we can get two different isomers forming. So if we imagine attack from one side, we'd give one isomer, attack from the other side, we'd give the other isomer. And because this is completely flat, it's equally likely that the nucleophile will attack from above as it is that it will attack from below. So that means when we get this attack, we're going to get 50% attacking from one side, 50% attacking from the other side. So that then gives us a racemic mixture of enantiomers. So a racemic mixture is where you get equal quantities of the enantiomers, and the enantiomers are molecules which are related as object and mirror image. So that's a bit of revision from Dr. Sarah Allman's course. So again, just to recap, in this mechanism, what we are saying is if we have a molecule and we lose the leaving group in the first rate determining step, we'll form a carbocation. Because the carbocation is planar, when our nucleophile attacks, it can attack from above or below, which gives us a racemic mixture. Now, I should point out that there are some parts of the course where you really should learn the specific mechanisms, and this would be one example of a mechanism that you should learn. We'd call this a generic mechanism because we're not stipulating what X, Y, or Z are. We're just saying for this type of molecule where we've got a leaving group that we lose in the first rate determining step to give a carbocation, which is then attacked above and below by the nucleophile to give a racemic mixture. This would be a generic example of the SN1 mechanism. What I've also done is I've provided sort of a walkthrough video for this mechanism where I've drawn it out in real time. So again, that's available for you on stream. So have a little look at this to go through exactly what I've said here, but with me drawing out each of the molecules, going to the intermediate, going to the racemic mixture. I've done it in real time, so you can hopefully see what's going on. Okay, so there's a little bit more we have to think about this mechanism. The first thing we have to think about is when might an SN1 reaction occur? Well, it's going to occur for molecules which have a good leaving group, because if it's got a good leaving group, that bond, if we go back, this bond here is going to be quite weak if we've got a good leaving group. So any molecule which has got a good leaving group is going to be able to do the SN1 reaction. The likelihood of it occurring is going to depend on how stable is this carbocation intermediate which it can form. Because if it can form a stable carbocation, then it's likely to want to lose that leaving group quickly to give the carbocation. If it couldn't form a stable carbocation, there'd be no reason why it'd want to form that. So SN1 reactions will occur where we've got a leaving group that we can lose and where we can form a stable carbocation, which is what it says here. We often think about rates of reactions because if we can understand the rate, then we can understand how we can actually influence how effective that reaction will be. And for a rate of reaction, we have to think which species are going to be involved in the rate determining step and which ones, therefore, if we increased the concentration of that species, would it have an effect on the rate? So again, going back, this rate determining step here is only dependent on the substrate. The nucleophile isn't involved at this step at all. This rate determining step is purely influenced by the loss of the leaving group from here. So that means that the rate will only depend on one species, and that's the substrate, which is another name for the starting material. And so when you think of a unimolecular reaction, remember this is SN1, substitution nucleophilic unimolecular. If it's unimolecular, there's only one species involved in the rate determining step, and in this case it's a starting material, it's a substrate. So the rate will be equal to a constant times the concentration of the substrate. It's independent of the nucleophile concentration. So make sure you learn this as a generic example of the SN1 reaction. Go through the walkthrough video just so you practice drawing it out yourself, sort of alongside me drawing it out. And this is what the rate equation will be. So I've said that it's very important for us to think about stereochemical consequences. Are we able to make a single isomer? Are we going to make mixtures of isomers? This is important, remember, because different isomers can have different biological and therapeutic properties. So if we think about the stereochemical consequences, we've said that what's going to happen is we're going to form a racemic mixture where we get equal quantities of each enantiomer. And this slide really repeats what we've had, what I've said on the previous slide, that when we look at the carbocation which is formed, this carbocation is planar. And so because it's planar, we can get the nucleophile attacking above or below, and that's going to give us 50-50 of the different isomers. So we're going to get a racemic mixture. So the stereochemical consequences for the SN1 reaction is that we're going to get a racemic mixture. So there's an exercise here which I don't run through because it's purely looking up definitions, and if you listen to what I've said over the last few slides, I have given these answers anyway. So please just remind yourself of what we mean by an enantiomer and what we mean by a racemic mixture. Go back through Dr. Sarah Allman's lectures, you'll find the answers there if you haven't picked it up from what I've said. So I've got an example here of an SN1 reaction where we're going to see it applied to a specific example. So remember, the one that I had before was generic. It could apply to any substrate that can undergo an SN1 reaction. What we're now doing is looking at a specific example. And the example we have, we're told that we've got this molecule here, and it's in a single isomeric form, a single enantiomer. It's in the S enantiomeric form. Again, you should be familiar with this R and S nomenclature from Dr. Sarah Allman's lectures. And we're told that if we were to take this molecule and we were to treat it under acidic conditions with water, then actually what we're left with at the end is a racemic mixture where we've got equal quantities of both enantiomer. So we should be able to rationalise this now based on an SN1 reaction. So you're told here it's an SN1 reaction. So we should be able to rationalise, based on what I've said from the generic mechanism, why we're going from a single isomer here, if we do the SN1 reaction, through to racemic mixture. So what's happening here essentially is we've got in the 1st step, if you remember, for the SN1 reaction, we get loss of a leaving group. So what we're doing is we're losing a leaving group. This is combining with H+ to make a good leaving group. This is breaking off to give us a carbocation. Remember that the carbocation is planar and it can be attacked from either side. So even though this was one enantiomer, we've now ended up with a planar carbocation. Because it's a nucleophilic substitution reaction, we have to think what's a nucleophile. And notice we're doing this reaction in the presence of water. Water has got a lone pair of electrons. So hopefully you remember from the previous part of the lecture where I spoke about definition of a nucleophile. A nucleophile is something which is either negatively charged or it's electron rich. So here with the lone pair of electrons, this will be our nucleophile, which will attack in the second step onto the carbocation center to give this. And then essentially this is going to be racemic because it can attack here from above or below. And then loss of H+ from here to give a stable molecule rather than having a plus which is unstable. We'll lose an H+ to make it neutral. That then gives us our product. And because this here is going to be racemic because of attack onto the planar carbocation, if this is racemic, this will also be racemic. So that explains why we go from one enantiomer. When we do the SN1 through a planar carbocation, we get a racemic mixture. So you might well have followed that. I hope you have followed that. But in case you haven't, again, I have got a walkthrough video for this, which you can look at on your Blackboard site on Streams. It will go through this exactly with all the arrows pushed in, showing the detailed mechanism. If you were to be asked to give an example of an SN1 reaction, you could draw out this. This is a generic mechanism which you should learn. So you should be able to draw this out, and going through this walkthrough video will help you. However, you would not be expected to remember a specific example like this, but if it was given to you, then you should be able to draw out and understand the mechanism as we've done here. Okay, so that's the SN1 reaction where we have loss of the leaving group in the first rate determining step. The only species which affects the rate is going to be the concentration of the substrate. The nucleophile is then involved in a second step, which is not rate determining. And because we have a planar carbocation, the nucleophile can attack above or below, which will give us a racemic mixture. That's a stereochemical outcome of the SN1 reaction. So these reactions we can do in the laboratory, we can use them to make drugs, but also they do occur in nature. So I've got an example here. Again, you would not have to draw this out. It's just to put the work in context. And what we're seeing here is there's particular substrates, particular starting materials that have got a biological leaving group. It's a diphosphate leaving group drawn out in full here. Basically, it's just a good leaving group. And what we see is if we have this substrate in nature, we could break the bond here to pull the electrons onto the OPP, leaving this carbon here deficient in electrons, so it's plus. This is a stable carbocation, so it's likely to form. And then the nucleophile in the second step can attack onto here to make a new bond. Now, the reason I've included this is this occurs naturally to give the fragrant smell of roses. And what people have done in the sort of perfume industry is they've taken these natural substrates to make the carbocation, and then they've introduced a whole range of different nucleophiles which could attack to give different molecules here which can have different fragrances. So it's an example of where this SN1 reaction has been used in nature and then in the perfume industry. Okay, so that was a run through the SN1 reaction where we lose our leaving group in the rate determining step to give a planar carbocation, and attack onto that from both sides is going to give us a racemic mixture of compounds. Now, it can be useful making a racemic mixture. For instance, if we don't know which particular isomer we might need in our drug discovery programs, but sometimes we do know what isomer we want. And in those cases, it's very useful to have a mechanism that will specifically give us the isomer that we want. Now, there's a second class of nucleophilic substitution reactions, which actually does allow us to make that particular isomer a single isomer in the reaction. And the second class of substitution reactions are called bimolecular nucleophilic substitution reactions, SN2. So substitution, nucleophilic, 2 for bimolecular. So in these SN2 reactions, these are now single-step processes. What we find, if you look here, our nucleophile is going to attack our substrate at the same time as our leaving group is going to depart. So in this bimolecular, 2 species being involved, our nucleophile and our substrate are both involved in that first rate determining step. Okay, so this here is a generic example of the SN2 reaction, and again, please learn this. What we've got is 3 different groups on this carbon. We just call them X, Y, Z, and we've got a leaving group. And what we see in this bimolecular reaction is our negatively charged nucleophile rich in electrons is going to push the electrons in here to make a bond at the same time as this bond is going to break so that the leaving group can depart. Now, because it's happening at the same time, we're going to get partial bond formation at the same time as we get partial bond breakage. So when we think about the mechanism, what we see is we get a transition state. So this symbol here is a transition state, and it's just some species that these go through on the way to the product. And what we've got here, you can see is dotted line. So we've got a dotted line for partial bond forming between the nucleophile and the carbon, and a dotted line for partial bond breaking between the carbon and the leaving group. The X, the Y and the Z are all still present. But because the nucleophile is attacking at the same time as that leaving group is departing, from a steric point of view, from when you think about the least hindered way in which the nucleophile can attack, it's going to attack from the side opposite from where the leaving group is. So attacking here has got more space, and then this can depart away. So if you think about that, if the nucleophile is attacking from the opposite side to where the leaving group was, it means we're actually going to get inversion in our final product. So here we are, our nucleophile is partially bonded, the leaving group is partially breaking away. When this bond is fully formed and this bond is fully broken, we end up with this species where our nucleophile is now on the opposite side to where the leaving group was. So when we have this SN2 reaction, as I say, this involves both the nucleophile and the substrate. We go through this transition state, which we can call a pentacoordinate. There's 5 groups around the carbon, so it's pentacoordinate trigonal bipyramidal transition state. And the product that we get at the end is inverted. We often refer to this as Walden inversion. So that's very important from the stereochemistry point of view. We get an inversion of stereochemistry, and if we have one isomer here, we'll get one isomer here. And as I said, that can be useful in drug discovery. Where we know there's a particular isomer that we want, we could make that using the SN2 reaction. So if you think about the rate of the reaction, in this case, because we have got the nucleophile and we have got the starting material substrate involved, and it's bimolecular, the rate will be equal to a constant times the concentration of the substrate, so that's this molecule, times the concentration of the nucleophile. Okay, so again, I've given you on your Blackboard stream site a live sort of version of this where I draw this all out from scratch, so that you should be able to follow it. And again, do learn this. This is a generic example of the SN2 reaction, and you would be expected to know this mechanism. Okay, so if we think about SN1 and SN2 reactions then, just as a sort of recap, what is the similarities and the differences between them? Well, the major difference between the SN2 and the SN1 excuse me, is that the SN2 reaction proceeds in one step via the transition state. So this is a one step. We've got the nucleophile attacking at the same time as the leaving group departs, and we're going through a transition state. Remember, the SN1 proceeded through 2 steps via a carbocation intermediate. So if I go back. Okay, so here it was, we lose the leaving group in one step to go via the carbocation intermediate. So that's the difference in terms of the mechanisms. In terms of the stereochemical outcome, the difference would be that the SN1 forms a mixture, a racemic mixture, whereas the SN2, we get an inversion of stereochemistry. So they're the differences. SN2 will lead to inversion of stereochemistry, whereas SN1 will lead to racemic mixtures. Okay, so I think I will leave that there for the second part of the lectures. If I could ask you please to just go back through that, check you're happy with a generic SN1 mechanism, a generic SN2 mechanism, and what is the stereochemical outcome of the two different mechanisms. And when we meet again for the next part, we'll go through some specific examples of the SN2 reactions to see how these have been used in drug discovery. Okay, good. Thank you.